So previously we learnt about new types of integrals. These are line integrals, and we looked at line integrals of the first kind. These are integrals of a function along a curve, and we saw that for those types of integrals, the direction along the curve that you take doesn't matter. Now we're going to think about what we can do for vector functions, and we find that we get a different type of line integral. This is the line integral of the second kind. Okay, so if we have a vector A with components ax, ay, and az, we can have the line integral along some curve C, let's call it C, okay? Then we have the line integral I that's taken along the curve C, and this time we have the vector A dotted with dr, where dr is some displacement along the curve. Okay, so A is given in components like this, dr is just dx, dy, and dz. Okay, vector and a vector. So this is just the dot product of two vectors. Okay, so this is just ax dx plus ay dy plus az dz. Okay, so effectively three different types of integral. Okay, the integral of ax dx plus the integral of ay dy plus the integral of az dz along some curve C. So this is a line integral of the second kind. Okay, so if we go from point A to point B, then the integral of A dot dr, okay, so this means going from A to B along the curve C, is equal to the integral. So let's think about going the opposite direction, from B to A dot dr. But this is not true. We need a minus sign here. Okay, so in this case, this line integral does depend on the direction which you traverse the curve. Okay, so if you go from A to B, then your dr points in this direction. But if you go from B to A, then your dr points in the opposite direction. Okay, so you need a minus sign to make them equal. Okay, so it depends on which way you go. All right. Okay, let's think about an example. And let's think about the work done by a force. Okay, so the work done by a force, in general, is given by the integral of the force dot dr, and you're going along some curve C. Okay, so you have a particle that moves along some curve C, and a force acts on it, and you're asking for the work done by the force. So the energy expended moving the particle along this curve. Okay, so probably with Gabriele, I think in section 7.5, you saw that the work done was equal to the integral of f of x dx. Okay, this is one dimension. So in 3 dimensions, it's just vector f, vector position. Okay, and a dot product. All right, so this is the general work done by a force. Okay. Okay, let's think about a constant force. So what does that mean? So we have the work done is equal to the integral of f dot dr, but f's a constant, so we can bring it outside the integral. So we have f dot, and then the integral dr. Okay, and we're going along some curve C. So let's go from point A, let's call it R1, to point B, and let's call that R2. Okay, so we're going to go from R1 to R2. And this is just equal to the force dotted with the answer to this integral. And this integral is just the integral of dr, which is just r. Okay, evaluated at the 2 points given by the limits, r1 and r2. So this is just f dot with r2 minus r1. Okay, which we call d. So f dot d. Okay, so this thing is d. Alright, so we find that the work done by a constant force is equal to f dot d, where d is equal to r2 minus r1. Right, so what does this mean? So r2 minus r1 is this vector that joins these 2 points. This is the d, okay? So we find that the work done only depends on the 2 endpoints. So this is the work done by a constant force, okay? So it's the case where f is constant. So the work done only depends on the 2 endpoints and not on the shape of the curve. Okay, so you could go along a different curve, like this, between R1 and R2, and the work done along this curve is the same, because the 2 endpoints have not changed. Okay, so for instance, if you think about the force of gravity, okay, I've got a pen here, the whole earth is pulling on this pen, so if I let go it will just fall downwards. Okay, so I can exert work against the force of gravity. Okay, and the work done, the energy I have to expend to bring this pen from here to here, the work done against gravity only depends on the 2 heights, the 2 endpoints, i.e. the starting point R1 and the end point R2. Okay, the change, or the energy expended against gravity is unchanged whether I bring the pen straight up between this point and this point, or if I do go around in a loop. Okay. Okay, the work done against gravity is the same. Okay, f dot d. So this is a dot product of 2 vectors. So you can think about a table, frictionless table. Okay, and here's a block of mass m, and gravity acts on this block. F equals mg, straight down. Okay, we're going to displace this block from this point, which we'll call R1, to this point, which we'll call R2. Okay, so d here is the vector from this point R1 to this point R2, and here the force of gravity dotted with d, f dot d, is 0. Okay, because f and d are perpendicular, because f is perpendicular to d. Okay, so the work done by gravity in sliding this block along a horizontal frictionless table is 0. Okay, because you haven't changed the height of this block. Okay, so at all points the force was perpendicular to the displacement. Okay, so this case in which the work done only depends on the 2 endpoints, the start point and the end point, and not on the path followed, not on the exact shape of the curve, is true for any case in which this A, can be written as the gradient of u, some potential. Okay, so let me clean up the board and we can show this. Okay, let's assume that A can be written as the gradient of some scalar potential, u. Okay. Then I, the integral, equals the integral of a dot dr, which is just the gradient of u dot dr. Okay, I'm going to put arrows here. Okay, the gradient of u is a vector. It's the vector a. Okay, so we've got a vector dotted with dr, which is also a vector, along some curve C. Okay, and we start at position R1, we move along some arbitrary curve C, and end up at R2. Now this thing just equals the integral of du between the two endpoints, R1 and R2. Okay, we'll show this in a second. And the integral of du is simply just u. So it's u evaluated at the two endpoints, so R1 and R2. U at R2 minus u at R1. Okay, and how can we see this? Well, let's think about what the gradient of u is. So the gradient of u is equal to du by dx, du by dy, du by dz. Yep. And dr we know is just dx, dy, dz. Okay, so the gradient of u dot dr, put arrows on this, is equal to du by dx times dx plus du by dy times dy plus du by dz dz. Okay, and this is nothing other than the total differential du. Okay, so that's what's used here. Okay, so the gradient of u dot dr is just the integral of du, which is just u evaluated at the two limits. Okay, so in this case, your line integral only depends on the values at the two endpoints and not how you got there, i.e. on the shape or the trajectory of the path you took to get there. Alright, and we saw in the last section that if you had a vector field that was irrotational, okay, that was potential, i.e. curl A was equal to 0, this meant that there exists a potential such that you can write A as the gradient of u. Okay, so if you have the curl of A is 0, then you can write this, and then the above is all true, okay, because this is what we started with. Okay, and we can actually use this to find the potential u. Okay, we take the integral of A dot dr between 2 points, some r0 and r. This will be this thing, u evaluated at r minus u evaluated at r0. Okay. So this tells us the potential at some arbitrary r. Okay, so let me rewrite space. So the potential at some arbitrary r is equal to the integral of A dot dr plus u evaluated at this arbitrary point r0, okay, which we choose. Okay, so this expression allows us to find the potential u, okay, that will give us A if we take its gradient. Now, if you remember, you can choose u up to a constant. So if you choose u as u plus some constant, then this doesn't change a. Okay, so we can just choose u of r0 to be 0, okay, as a convention, and then we just have this thing. So our potential at r is given by the integral from r0 to r of a dot dr, where it's understood that the potential at r0 is equal to 0. Okay. All right, so this links some things from section 3 and 4. Okay, but don't be intimidated. We have a vector, another vector, we've got a dot product. Okay, we know what a dot product is, it's this. We're going to do an integral. It's a line integral, so it's along some curve. So at every point on the curve, we're going to think about what a is, okay, and what a dot dr is. So maybe a is like this, dr is like this at this point. At this point, a may be like this, dr like this. Okay, we just add up all the a dot drs as we move along the curve. Okay, but if a is irrotational, i.e. the curl of it is 0, then a can be written as the gradient of some potential. And if so, then the value of the line integral, it's easy. It only depends on the two endpoints, or the starting point and the end point, and not on the path you take to get there. Okay, and then we can use that fact to actually work out what the potential is. So this is the potential at any point in space, 3D space, and it can be worked out as the line integral of a dot dr. All right, okay, so let's think about an example where we actually calculate this potential. Okay, so we're given a, we're asked to do the line integral, and we calculate this potential. All right, let's think about an example where we calculate the potential. So let's think about a vector field that is given by, so the components of this vector are yz, xz, xy. Okay, so this is a vector that changes everywhere you move in space, and depending on where you are, the x, y, and z components, the components of the vector are yz, xz, and xy. We want to do two things. Show that A is irrotational, or potential, i.e. that curl of A equals 0. Okay, and then we want to find the potential. Find the potential. Okay, because as we saw previously, if curl A equals 0, then there exists some potential u for which A is the gradient of u. Right, let's think about number 1 first. So curl of A. So curl of A is equal to, so let's remember we do this determinant, and we've got, for the nabla, we've got d by dx, d by dy, d by dz, and then we've got the components of A, so that's yz, xz, and xy. So curl A is equal to, so to get the first component, so this is a vector, curl A is a vector. To get the first component of the vector, we hide this first column, and we do d by dy of xy, d by dy of xy, minus d by dz of xz. So that's this minus this. Okay, remembering to keep the differential operator on the left-hand side. So that's the first component of our vector curl A. The second component, let me write it as a column vector. The second component, we cover up the middle, and it's now d by dz of yz minus d by dx of xy. Okay, and then the final component of our vector, we cover up the last column, and we've got d by dx of xz minus d by dy of yz. So our vector has three components. D by dy of xy is just x. D by dz of xz is just x. So we've got x minus x. That's the first component. D by dz of yz is just y. Minus d by dx of xy. So that's minus y. And then finally we've got d by dx of xz, which is z, minus d by dy of yz, which is minus z. Okay, so this is 0. So we've shown that curl A is 0. Okay, so it's what we find, it's x minus x, y minus y, z minus z, i.e. it's the 0 vector, 0, 0, 0. Okay, here I wrote it as a column, here I'm writing it in a line. All right, so this A, where is it? Here. This A is irrotational. And because of that, it means that we can write this A as the gradient of some potential U. And the second question is to find what this U is. Okay, so let me rub this off. Okay, so now we're going to find the potential. Right. So we know that A is equal to the gradient of U. And we saw that this meant that we can write U of R as the integral of A dot dr from some R0 to R, where it's understood that U evaluated at R0 is equal to 0. Okay, this is our convention. Right, so this is how we calculate our potential. So in this case, what is A dot dr? Okay, it's here. It's equal to the integral of ax dx. So it's the yz dx plus the integral of ay dy, so xz dy, plus the integral of az dz, x, y, dz. Okay, we've got to take it along some curve. And in this case, as we showed, it doesn't matter which curve we choose. All that matters is the endpoint. Okay, so let's choose the curve to find, so we want to find the potential at some coordinate r. Okay, r has coordinates x, y, z. So let's get there by going along x, then along y, and then along z. Okay. So we go from the origin to the point 1, 0, 0 to the point 1, to the point x, 0, 0, then to the point x, y, 0, and then to the point x, y, z. Alright, that's going to be our curve. Alright, so let's look at these integrals along this curve that goes from the origin to this point x, 0, 0 to x, y, 0 to x, y, z. So let's focus on the first one. It's got a dx. Okay, so dx changes along the first part of the curve, this bit. Okay, but from this point to this point, x doesn't change, so dx is 0. And from this point to this point, x doesn't change either. Okay, because it's only z that's changing along this bit. So this integral along the full curve is given by just the integral along this section of the curve. So this is the integral of yz dx from the origin, x equals 0, to the value of x equals x, big X. Okay? Then we've got the integral of x, z, dy along the curve. And dy is only non-zero in this middle section. Okay? Where we go from y equals 0 to capital Y. Along this part, it's only x that changes, and along this part, it's only z that changes. Okay, and then this integral, x, y, dz, along the full curve, so along all three sections, is only non-zero along the final section, where dz is non-zero. Okay, this first section, you're stuck in the xy plane, so you don't change z, and then you move from y equals 0 to y equals capital Y, again in the xy plane, so dz is 0. So it's only this final section, where z changes from 0 to capital Z. Okay? Now, we can think about what the values of y and z are as well. We haven't done that. So this first section, from 0 to x, okay, y equals 0 here. Okay, so y equals 0. Sorry, and z equals 0. Z equals 0 and y equals 0. Okay, so this is the integral of, so this is yz integral dx. This is 0. 0 plus the integral of x, z, dy along this section. Here x is not 0, but z is 0. Okay, so we get 0 for this term. And then finally we've got this section where x is not 0, y is not 0. Okay, but x here is equal to big X, y is equal to big Y. So we've got plus the integral of x, y, dz between 0 and z. And xy, that's just a constant. X, y, integral dz between 0, capital Z, which is just x, y, z. Okay, so this is the integral of a dot dr, this thing. Okay, that's our potential u. Okay, so we found that the potential at the point x, y, z is just equal to the product of x, y, and z. All right, and you can check that the gradient of this potential u is equal to a. And I'll leave that as an exercise for you. Okay. Okay, so here's an example where we found the potential by doing the line integral explicitly. And again, we could have chosen any path. We've just chosen this path. This makes things easier because we have dx and dy and dz 0 along 2 of the 3 sections. Okay, but you could have chosen any path to get from the origin to the point x, y, z. You'll get the same result. Okay, that the potential at the point x, y, z is given by the product of x, y, and z. Okay, good. All right. So on to section 4.3.